Okay, my name is Ignaz Kohlbecker. I'm engineering consultant based in Switzerland, and I'm dealing with software engineering projects most of my time, so not really related to high-performance computing, more of the things model people like me do. In this talk here, I will show about the slide number format, which I related maybe most close to the type 1 unums, with some variations that I think may be worth discussing. So when we think of a simple arithmetic expression that we encounter in engineering applications, then they contain both exact rational numbers and inexact quantities, which typically represent something that has been measured and is only known to a certain precision. And we may want to represent that with intervals. And when we want to get into the verification of numerical results or into the analysis of numerical algorithms. So when a longer computation is going on with such values, then we are very unlikely to hit any of the exact rationals anymore. We will end up somewhere within some intervals that we will have as an intermediate or our final results. That raises the concern that all the exact rationals in the number system may be underused in realistic situations. So in order to implement such expressions as given up there, I think there's two ways to do that. One is to have as many as possible rationals in the number system and convert them by the compiler into such a number and then work with that. Or, as I propose here, we have a separate set of arithmetic operations that work with the exact integers and then treat integers as integers there. If we could achieve something like that, then we could remove all the exact values from the number format. If we do that with the type 1 unum, then we are actually gaining 1 bit because we can make the u bit something like a hidden bit. This is thinking of merging the exact rationals with one of the adjacent interval. We can use the gain bit to improve the accuracy by a factor of 2 or to even square the value range of the number format. The second characteristic of the slide number format is kind of enabled by the first, but basically independent from that. Is that of once we are not searching for representing exact rationals anymore, we are relieved of trying to only approximate the logarithmic scale. We can actually go to the perfect logarithmic scale and then start storing the exponent of our power functions, which leads us to a logarithmic number system. They are known for a long time and have some nice properties regarding multiplication, division, power functions, and square root function. But of course, they also have a painful penalty for addition and subtraction. What's nice here, similar to type 2 unums, we can design them for being closed under reciprocation. And maybe one additional point I want to make is the choice of the base here. Coming from a more practical application side, I see advantages to use base 10. I see advantages in the conversion to and from the human readable format. And that probably happens much more than we would like to have. Serialization and deserialization of data happens all over the time. And there is some side effects I want to show here with one example. We don't have to go in all the details, but imagine a critical system like in clinical diagnostic, a medical application, and you have a measurement value that is transferred from a sensing device to a computer through some bus system, and it happens to be that this is going to be a string and it gets parsed. Now imagine this value needs to be compared with a threshold value to make a critical decision, which may be a dead or alive question. But unfortunately, the threshold value is inserted in millis of your unit, like 1,000 times more. That could be in order to save entering a lot of zeros to the operator that needs to configure the system, or it could be some domain-driven requirement, some regulation which is outside of our decision. So then we need to either divide the threshold value by 1,000 and compare with the actual value, or do the inverse and multiply the measured value by 1,000 and compare with the threshold value. What happens with float here is that this can go wrong. In the one case, you get another result than in the other one. And if we have a base 10 logarithmic system, as I propose here, then the sequence of decimals, like in this example, 1885, always leads to the same representation in the mantissa, independent from the decade that you are actually in. And that may have some advantages here, because our engineering world is base 10 and not base 2. So there's nothing broken here with the floats. They perfectly behave as designed. This thing slips in just because of the conversion between base 2 and base 10. And what's bad about that for software engineering, you would never suspect this number 1885 to be in any way special or being a corner case. So any software testing will always fail and not find these cases. And even if they appear in the field and are reported back, they may cause a lot of frustration because people are not believing that something is going wrong here. So now how does it look like? The slide value, the slide number format arranges the intervals as shown here. So we have half-opened intervals, and the open endpoint faces towards the ones. So there's only 3 exact points, 0, 1, and -1. And in between there the regular values as half-open intervals. There's overflow values towards the ends of the number line, but there's no infinity because there's no infinity in reals. There's a special value, the empty set. If we think of dividing the real number line into sets, then we need an empty set as well. That is being used for empty solutions, like an inequation that has no solution for reals but is well defined, or for things that are simply not defined for reals, such as division by 0. I'm not going into all the details of a formal definition, just want to point out one thing. You see all these tick marks here. I call them the anchor points that are the anti-logarithms to this exponent that we actually store in the number format. So there's only 2 special values, 0 and the empty set, which are enumerative in the sense that a bit pattern is just assigned to their value. And for all the other values, we have one closed form to express this anchor point. And that is the thing we actually need to compute with. It looks about like this. So the mantissa values always fill one decade, or at least the anchor values do. For values above 1, you see this particular offset of the range that is covered by the intervals. So all the slide values are unique. There's no redundant representations, no subnormal values, and we have nice properties for closeness, for negation, absolute value, and under reciprocation. The overflow and underflow intervals are the reciprocals of each other. Now, from the general to some more concrete slide values, the 32-bit slide values. I show a few examples here of concrete values. So everything 0 is 0. Mantissa 1 is the underflow, and the first regular value is with Mantissa 2. Comparing these 32-bit slide values with IEEE floats, the floats shown in orange here, we see that the dynamic range for all the values that exist, they show this particular tail here for the subnormal values, and as in a close-up you see that it's not a straight line, it has this wobbling, which is not the case for the slide values. The slide values lie on a straight line, so it's very simple behavior here in that. And the dynamic range is larger than that of the floats, which I think is beneficial, so because no float value would saturate into the overflow of when it is modeled by a slide value. For the relative error, similarly here the value range is larger, and it's a complete flat line for the slide values, which is nice. In contrast to that, the float values, they have this wobbling band at slightly better values, but you have a complete degeneration for the subnormals. Now, similar to U-bounds, we can pair two of these values to start expressing larger intervals, and also special combinations of other endpoints for the minimal intervals. So the first part here uses the order as an extra bit of information that we can use to encode other endpoint types. So we can have two open endpoint types, and then we can take some of the special values like overflow and empty set to extract things like the anchor point and to have the open intervals between the anchor points. As you probably see here, we cannot express everything. Not every combination is possible. But as I would argue, we have a pretty rich expressiveness, because for longer ongoing computations, we would expect to have a majority of open intervals, and they can be expressed here. What we cannot express is two closed endpoints and inverted endpoints compared to what the individual slide values in here deliver. So there's a design trade-off. We can squeeze out two more bits for the more probable values to occur, but we need larger data structures than for the more rare cases. So that is an engineering trade-off that is open to discussion. Now, conversion to and from human readable form. I want to show this slide here is the way we should write real numbers is using a multiplication sign padded by the thin spaces. We should group the decimals also separated with thin spaces. So there's a couple of rules that are formalized. They're standardized by the Office for the Système International in Paris. When we looked 30 years ago what computing machines were able to do, it looked more like this, not really readable. Unfortunately, that was the year when the first draft of Unicode was proposed. Unfortunately, 30 years later, it still looks the same when we serialize floating point values. And I suggest that it's about time to do better in this here.
It was 40 years ago. Right?
Yeah.
That was 1978.
88.
For Apple II.
At least that was the time I was still exposed to these kind of machines. Yeah, maybe I was a bit behind of time. Yeah.
He came out in 1977.
Yeah.
We were at Macintosh, that's why 1988.
Okay. Yeah. So the objectives here for having the serialization and deserialization methods implemented in a .NET library for 32 bits was I wanted to have the round-trip safety, full portability between and with bitwise identical outputs on other machines. It should be compliant with this international system, but still allow the culture-specific customizations to have multi-car Unicodes and all these things that you need in other languages. By having this richer feature set, it should still be performant, comparable to what the .NET system offers. So this requires, the two-string method requires computing 10 to the power of r. And there's two implementations compared here. One uses a Taylor series approximation, and one uses a piecewise linear approximation. For the Taylor series approximation, I show a mathematical prototype that actually uses arbitrary size integers. That needs up to 8 summands if we divide the range into 8 starting values. For the slide values, there's a slightly different criterion. I wanted to have 8 decimals of any value that is inside the interval. So when I give out a value, I do not want to round to a value which is outside of the interval. Normally that is only one, single one for 8 decimals. Sometimes there's a few that are available. So it's a little bit looser. That's why it's possible to achieve that with 7 summands. The implementation takes about 150 lines of code with one loop and 67 lookup values. The piecewise linear approximation was presented many years ago for base 2. Porting that to base 10 and the much higher accuracy that we have here, we don't need 11 intermediate points. We need actually 23,000 pre-computed powers, which is quite a lot. That can be optimized by splitting that into a product, and then we end up with 308 pre-computed powers. This implementation takes only 9 lines of code, has no loop, but in contrast has a lot more of lookup values. The performance shown here shows in blue here you see the Taylor series approximation, which is already about twice as fast as the standard .NET implementation for floats, and you gain another about 10% of performance for the piecewise linear approximation, but for the price of having almost 5 times as many lookup values. For the try-parse method, it was not actually possible to beat the float. It is about 2/3 slower than that, but has a richer feature set in terms of what it can actually parse and recognize as a number. To conclude, I could show that the slide number format can gain 1 bit for smallest intervals, or can gain 2 bit for the more probable of the larger intervals. And we should expect less side effects and corner cases by using the perfect instead of only an approximate logarithmic scale. And I showed with that example that base 10 also is beneficial in some special cases of conversion to and from human readable form. The performance did not degenerate for having the overhead of this number format. It was possible to be within the range of what we know from the .NET world, while still also paying attention to some modern typography. So I think it is a good starting point for getting more towards understanding numerical algorithms, analyzing them, and getting verified results. Thank you.
So we have time for questions?
I hate to be the guy who always asks the question.
One puzzle is if these are half-open intervals, do they always face with the lower number is always closed and the upper number is open? Or is it, because if you flip it, if you negate a number, what do you do?
For negation, it works, yeah.
So it inverts, so they face away from zero. The closed end is always closer to zero.
Yeah.
Are there any inconsistencies you get from, like just even adding a number to its negative then?
Yeah, there is cases where this fails also, yeah. For example, if I multiply with a scalar integer and then cross the boundary of 1, then I don't want to invert the endpoint types, and then I have to already resort to a larger data structure that can express that. Yeah.
So I have a question. So there are obviously some similarities with type 1 unims here and U-bounds. Have you had a chance to look into how they perform, how they compare?
Not yet, no.
Okay. So
What could be the error approximation model, for example, basic operations, addition or subtraction and division, at what, let's say, slide 32-bit format? So at what bit one has to truncate?
I'm not sure if I
So in floating point number,
yeah.
you have an error approximation model. Let's say you have both algorithm. So for example, for 32 by 32, then you have 64-bit. Most paper says that you have to truncate at 56 bits or 57 bit. You do the normal rounding operations. So how, in this case, slide 32-bit format? Focused on the basic arithmetic operations.
Yeah. So for basic arithmetic operations, when we do that with these numbers here, for multiplication and division, we will always land on another value that is exactly representable here. So I don't see any issue of rounding. If I got you correct, you were asking for the roundings, yeah. And for the addition and subtraction, I'm afraid I cannot answer your question yet because I have not investigated it. Yeah.
any other questions? Here's one.
It's good to see another .NET app here. Is there any specific reason you went with the .NET platform, or is there any specific reason you went with the .NET platform, or that's just what you had and you tried it?
Not in particular. It's more that this is the world where I live in most and where I would like to see the application of that. Yeah.
Thank you.
Yeah.
Okay, if there are no further questions, let's thank the speaker again. Thank you.
Thank you.